In question number 6, it says that two spheres A and B of equal radii r each are uniformly dense with densities 2 rho and rho respectively are placed as shown in figure. The initial acceleration of particle placed at point P due to gravity of both the spheres will be. So there is this particle m0. We have to find the acceleration of this particle. So to find the acceleration, we need to find the net force on this particle. So first we will calculate the mass of each sphere. So since the radius is r and density is 2 rho, so we can say that the mass of the first sphere will be equal to 2 rho into 4 by 3 pi r cube. Similarly, mass of the second sphere will be how much? That will be equal to rho into 4 by 3 pi r cube, because the density is rho. So now we know the masses. And what is the distance of the particle from the centers of each sphere? So this whole distance is 4r. So we can say that the distance of A from m0 will be equal to 3r, and the distance of B from m0 will be equal to r. So force due to the first sphere, that will be F1. So what will be the value of F1? So F1 can be written as G into mass of the sphere 1 into mass of the particle divided by distance square. So if I put the values of m1 here, so you will get G into 2 rho into 4 by 3 pi r cube into m0 upon 9r square. So that will be equal to the 8 by 27 rho pi r m0 into G. This will be our F1. Similarly, if I say that force due to sphere B is F2, so F2 will be how much? F2 will be equal to G into mass of the sphere B into mass of the particle divided by distance square. So if I put the value of m2 here, so you will get G into rho into 4 by 3 pi r cube into m0 divided by r square. So by solving, we will get 4 by 3 G rho pi r m0. So this is the force of F1 and F2. And since F1 and F2 are opposite, so we can say that our magnitude of the net force will be equal to the subtraction of F1 and F2, right? So if I put the values here, you will get 8 by 27 minus 4 by 3. We have to only calculate the magnitude, right? Into G rho pi r m0. So when you will solve this, you will get 28 by 27 G rho pi r m0. So this is our net force, but we have to calculate the acceleration. So we know that the acceleration will be equal to the net force divided by the mass of the particle. So when you will divide, you will get 28 by 27 pi rho g r. So we can say that our option number 3 will be the correct choice. Now let's move to the question number 7. In question number 7, it says that the change in gravitational force experienced by a particle of mass m due to a uniform thin circular ring when moving the particle from center of ring by a distance x along the straight line perpendicular to the plane of the ring is proportional to. So according to the question, we have to calculate the change in gravitational force experienced by a particle of mass m due to uniform thin circular ring. We know that if there is a ring of mass capital M and radius capital R, so the gravitational field at a distance x from the center along the axis will be given by the formula G mx upon r square plus x square whole to the power 3 by 2. This is the formula of the gravitational field due to a ring, right? So what will be the force if I place a particle of mass m here? So we can say that our force will be equal to gravitational field into mass. So that will be equal to g m m x upon r square plus x square whole to the power 3 by 2. Since x is very less than r, so if I use the approximation method and if I take a common r here, so you will get r cube 1 plus x by r whole square whole to the power 3 by 2. Since x is very less than r, so x by r can be taken to be approximately 0. So we can say that our force at a distance x will be equal to g m x upon r cube. So this is our force. We know that at center gravitational field is 0. So the force will be 0. So the change in the magnitude of the force will be simply g m by r square into x minus 0. So that will be equal to g m by r square into x. And since this whole quantity is a constant, so we can say that our change in force will be directly proportional to x. So my option number 1 will be the correct choice. Now let's move to the question number 8. In question number 8, it says that a satellite is revolving very close to the Earth's surface in a circular orbit, has potential energy U. Find the change in mechanical energy if it is made to move away from Earth such that its velocity becomes half while going around the Earth in a large circular orbit. So that means initially it was moving in a circular orbit very close to the surface. Now it is moving away from the surface such that its velocity will become half. So we know that if this is our Earth, right, having radius capital R, mass capital M. So initially the satellite is revolving very close to the Earth's surface. So initially the satellite was very close to the surface of Earth. So we can take the radius of the orbit of the satellite initially will be equal to R. So the potential energy initially. So initially the potential energy U initial will be equal to minus g m by r. But according to the question, this is given as U. And what will be the total mechanical energy? And the total mechanical energy initially will be equal to minus g m by 2r. That means U by 2. This is our initial mechanical energy of the satellite. Now since it has taken up to some height such that its velocity becomes half. So we know that the orbital velocity initially will be equal to how much? Root under g m by r. But according to the question, finally the velocity VO dash becomes half of the initial orbital velocity. So that means root under g m by r final will be equal to 1 by 2 into root under g m by r, the initial velocity. So we can say that our final distance from the center of the Earth to this satellite will be equal to 4r. So this is our final distance of the satellite. So we can say that our final mechanical energy will be equal to minus g m by 2r final, and that will be equal to minus g m by 8r if I put the value of r final. So this is our final. But minus g m by r is equal to U, it is given in the question. So we can say that our final total mechanical energy will be equal to U by 8. So this is our total final mechanical energy and this is our total initial mechanical energy. But what we have to calculate? We have to calculate the change in its mechanical energy. So the change in the mechanical energy will be equal to the final mechanical energy minus initial mechanical energy, and that will be equal to U by 8 minus U by 2, and when you will solve it you will get minus 3U by 8. So we can say that our final answer will be minus 3U by 8. So our option number 4 will be the correct choice. Now let's move to the question number 9. In question number 9 it says that ratio of escape speeds from the surface of two uniformly dense planets of densities rho and 2 rho respectively having equal radii. We know that the escape velocity from any planet will be equal to root under 2gm by r. So there are two planets having different densities but the radius is same. So we can say that our masses will be different. So if I want to find the escape velocity from planet 1, that will be equal to root under 2g mass of planet 1 by radius r. So if I put the value of m1 in terms of the density, we will get 2g into rho into 4 by 3 pi r cube divided by r. So that will give you square root of 8 by 3 g rho pi r square. This is our escape velocity from planet 1. So now if I calculate the escape velocity from planet 2, similarly, since the density is doubled, so we can write root under 8 by 3 g into 2 rho pi r square. Everything remains same, only density changes and it becomes double. So the escape velocity will become like this. But what we have to calculate? We have to calculate the ratio of escape speeds. So that means VE1 by VE2. So if I calculate the ratio, so since all things remain same, only here it is rho, it is 2 rho. So we can say that our ratio will be 1 by root 2. So our option number 1 will be the correct choice. Now let's move to the question number 10. In question number 10 it says that for a satellite going around Earth in an elliptical orbit with the Earth at one of the focus of the ellipse, select the incorrect statement. Again we have to calculate the incorrect statement. So we know that if Earth is at the focus of the ellipse and the satellite is revolving in an elliptical orbit, then the force on the satellite will always be towards the Earth, gravitational force. So we can say that the torque of the force must be equal to 0 about the Earth, right? So we can say that torque acting on a satellite about the center is always 0. Yes, this is the true statement. Second statement says that the aerial velocity of satellite about the Earth is inversely proportional to the mass of satellite. So we know that from the Kepler's second law, the aerial velocity of the satellite will always remains constant. It will be equal to L by 2m, and we know that angular momentum is defined as the mvr divided by 2m. So mass will cancel out, so you will get vr by 2. So aerial velocity is independent of mass. So this is our false statement. Now third statement says that the magnitude of angular momentum of satellite about the center of Earth remains constant. Since the angular momentum will remain constant only if the torque is 0, but we have seen that torque is 0, so we can say that angular momentum about the Earth will be constant. So this is also a true statement. Fourth one says that kinetic energy of satellite does not remain constant, and we know that since the distance is increasing and decreasing, so the product of the velocity and distance will remain constant. So if the distance increases, velocity will decrease, and if the distance decreases, velocity will increase. So the speed of the satellite will not remain constant. So we can say that kinetic energy of satellite does not remain constant. So this is also a true statement. So from this we can say that our option number 2 will be the correct choice. Now let's move to the question number 11.